Good morning, everyone. My name is Ioanna Malliaroudaki, and I'm an early-stage researcher in PROTECT International Training Network, based at the University of Nottingham, in the Food Water Waste Research Group. In FoodSim 2020, I'm participating with a mini paper entitled Considerations in Modeling the Energy Demand in the Dairy Supply Chain. These are the contents of my presentation. Firstly, I will provide you some introductory information. Then follows the aim and objectives of my study, and finally I will present you my modeling approach, and we will have a discussion section. The greenhouse gas emissions of the dairy sector are mainly derived from the extensive fossil fuel usage and the cow's intestine fermentation. In fact, in 2015, the dairy sector emitted 1,700 million tons of CO2 equivalent, which is 80% higher than that of 2005. Moreover, milk production, processing and transportation accounts for about 2.7% of total anthropogenic emissions. According to the European Green Deal, the net emissions of greenhouse gas emissions should be nil by 2050. Thus, energy use reduction, recycling and waste management techniques should be implemented to the entire dairy supply chain. However, the dairy industry is going to face many challenges in the future. More specifically, the fast-growing world population might lead to a significant rise in dairy products demand. Moreover, warmer climates caused by climate change might affect the crops for animal feed yield, and the higher temperature might cause heat stress to cows, leading to decreased milk production and increased mortality risk. Moreover, foodborne pathogens might develop heat resistance, which raises concerns on food safety. This situation might have serious consequences on the energy utility. More specifically, the higher food demand might lead to a proportional increase of energy for production and transportation and refrigeration, while the food safety measures that might have to be implemented will affect the energy, since they might need more intensive pasteurization and lower refrigeration temperature, which are really energy demanding processes. Here are presented some numbers related to the energy demand in the dairy supply chain. Regarding the energy mix in farms, we can observe a high energy demand in diesel, which is about 69%, and around 70% in electricity. It is clear that these sources of energy should be replaced by renewable resources. Moreover, the most electricity demanding processes are milking and cooling. Below is an example of energy requirements for the transportation, processing and storage of 1 kilogram of Gouda cheese. The table shows data from two different cases of production in mainstream food systems and in local food systems. The total amount in both cases is around 35 megajoule per kilogram of cheese. This value is relatively high, consider that in this amount of energy equals to the energy released from the burn of 1 liter of diesel. In the mainstream food system, processing and storage require higher amount of energy compared to that of transportation. This is probably due to the high automation that require electricity in the large manufacturing plants. On the other hand, in local food systems, transportation requires the most energy compared to processing and storage. This is probably due to the possible secluded location of the local dairy that may lead to longer transportation routes. On the right above, you can see a figure showing the energy needs for different dairy products in terms of electricity in blue and in fuel in orange in a processing plant. We have fresh products such as cream and milk, and long-life products such as milk powder and concentrated milk. It is clear that the energy needs per kilogram of fresh products is much less than that of long-life products. Moreover, the average energy mix of fresh products is about 50% of electricity and 50% of fuel, and for long-life products, only 8% of electricity and 92% of fuel. The relatively higher electricity needs of fresh products is due to their extensive refrigeration needs. while the extensive fuel needs for long shelf-life products is due to their extensive processing. Finally, this pie chart shows the share of energy needs in a manufacturing plant. We can observe that cleaning in place this process has the biggest contribution in energy share, and then follows filling and packaging and pasteurization. Especially for these processes that have the biggest share, more energy conserving operations should be implemented. Overall, my research project aims to develop tools to estimate the farm-to-fork energy use in the dairy supply chain and to understand the impact of climate change on the energy utility by simulating future climate change scenarios. The objective of my study is firstly to develop a holistic mathematical process model of the dairy supply chain that can capture the mechanism and output of each supply chain stage. Secondly, I aim to estimate the energy demand of each supply chain stage for single and multi-products. And finally, I will simulate different future climate-based operational scenarios of the dairy supply chain. After reviewing existing food or dairy supply chain models, we came up with some conclusions. Most supply chain modeling work is done due to its significant importance in the marketplace and since any changes in the supply chain could entail a major capital. The main reason of modeling is for logistic and refrigeration optimization, quality improvement, and long-term stability. The main inputs used are time, temperature, and cost. As mentioned in a study, the dairy processing industry needs more tools and programs to reduce energy demand. Moreover, some review work done in supply chain modeling indicate that simplified models should be used to facilitate the optimization process. The models should provide the ability to simulate multi-product manufacturing and distribution. There is a lack of work done in supply chain modeling that includes sustainability and food quality indicators. And finally, it is important to incorporate sensitivity analysis techniques in the models due to the great variation rates of parameters in the supply chain. Here, I will present you the methodology of the modeling we are going to follow. Firstly, we are going to sequence the dairy supply chain into stages. Each stage will be modeled separately as a unit operation. Secondly, we are going to develop or use existing energy models for each supply chain stage, which will be based on mass and energy balances, or when these are not applicable, we are going to use data-driven models instead. The next step is to combine the models properly in a holistic energy model. This should be done by considering the losses in mass and energy in all stages. Finally, model simulations will be applied in order to estimate the farm-to-fork energy demands of a unit of dairy product in a certain supply chain scenario. The inputs of these models will be the mass input, how much milk is needed, the time duration, the process conditions, such as temperature and pressure, environmental parameters such as the ambient temperature, and in that way we could include the climate change effect, the material composition to use the same models for different products, the type of equipment and the scale of production, while the outputs will be, of course, the mass output, which will be a unit of dairy products, such as 1 kilogram of cheese, and the main output, which will be the energy demand per unit of this product. Also, these models could give information for the energy mix, so how much electricity and diesel and other resources are needed for the production and the entire supply chain. And finally, the models could provide information about the rate of mass and energy losses per process. During the development of the holistic supply chain model, we have to deal with an important challenge. We have to find a balance between modeling in a high level of detail to achieve accuracy of results and at the same time develop a convenient enough model that allows the application of simulations and optimization techniques holistically for the entire supply chain. Keeping note that the level of detail in the models will depend on the contribution of that stage in the total energy consumption. Thus, for example, in the manufacturing plan, each process with important contribution will be modeled separately. Overall, the development of the holistic mathematical process model has the following benefits. Firstly, simulation can provide a complete overview of the energy needs. Secondly, the model allows the identification of the most energy-consuming stages of the supply chain. Moreover, it allows the evaluation of alternative operations and the comparison of different supply chain scenarios. Finally, the model could be upgraded to a decision-making tool for changing related to optimal temperature conditions for storage and transportation. All in all, this complete model has strong potential for improving sustainability across the dairy supply chain. Thank you very much for your attention. Please let me know for any questions.